Okay, problem 1 from the written team problem set says you have a 0.7 kilogram mass, and it's on a frictionless surface, and it's attached to a spring, and it's oscillating horizontally, and it gives you this graph. And it says the displacement x of the object as a function of time is shown in the graph. With the aid of the graph, determine A, the amplitude of the motion. So we're just going to look at the graph. Here's the graph. It goes something like this, and the top of the motion, this is sometimes called the semi-amplitude because it's halfway from the top, from the crest to the trough, but we call it the amplitude, 0.080 meters. So A equals 0.080 meters. That's that done. We're asked for B, the angular frequency, omega, which is equal to 2 pi over the period. So we have to figure out the period, and we know that right here is 4.0 seconds. So that's where the motion repeats. So I would say that period equals 4.0 seconds. So omega equals 2 times pi divided by 4. So typing that into my calculator, 2 times pi divided by 4 equals omega equals 1.571. This is in radians per second, and let's not forget our significant digits, which looks like it will be, probably about 2. Everything seems to be given to 2, so let's call it omega equals 1.6 radians per second. Part C of problem 1 asks for the spring constant K. All I can think of for this is that we know that omega equals the square root of K over m for mass on the spring. So let's just solve that for K. And we got that omega squared is equal to K over m, and K equals m times omega squared. We're going to take the omega from previous. Let's actually look at what the mass was. Mass is 0.70 kilograms, and omega was 1.571 radians per second. We'll square that. Type that into my calculator. 0.7 times 1.571 squared is equal to 1.727, and this is in newtons per meter is what the spring constant always is. Let's not forget significant figures. Let's do it to 2, 1.7 newtons per meter. Part D is asking for the speed of the object at t equals 1 second. Well, that I'm going to get from inspection on this graph. At t equals 1 second, the object is at maximum x. It's as far to the right as it's going to get. So it looks like this. And here, the slope at the maximum equals 0, so the speed equals 0. And the magnitude of the object acceleration at t equals 0 seconds, well, this will be the maximum. So at t equals 1.0 second, the object, or the mass, is at max displacement. As we've just said, it's stopped also. So it has So maximum force, because force is equal to the spring constant times displacement, and so maximum acceleration. And we have an equation for maximum acceleration. I think we have that A max for simple harmonic motion is equal to A times omega squared. So the amplitude, I think we already solved for that somewhere. Back up here, let's scroll. Amplitude was 0.080 meters. 0.080 meters times the omega, which we had from part B, 1.571 radians per second. We're going to square that. We're going to end up with an answer of meters per second squared, 0.08 times 1.571 squared equals 0.1974. That's meters per second squared. Let's not forget significant digits. 2 will give us 7, rounds this up to a 0 and this up to a 2, so it's going to be actually 0.20 meters per second squared. It's two significant figures.